So in Chapter 3, Section 2, we're going to start by talking about domain and range of a function. And as we know, the domain is the input values and the range is going to be our output values. So the first way we want to analyze domain and range is going to be graphically. So for continuous functions, the domain is smallest x to largest x, and the range is smallest y to largest y. And we're using x and y for our domain and range values, so the x's are our inputs and the y's are our outputs. So the key thing here is a continuous function. And we're not going to give a super precise definition of continuous at this time, but for our purposes, it's good enough to visualize continuous functions as follows. A function is continuous if you could draw its graph without ever having to lift up your writing implement. So if you could draw it by only having to put your writing implement down once and draw the entire curve until you're done, then our function is continuous. If that's the case, the domain is going to be our smallest x value to our largest x value, and the range is going to be our smallest y value to our largest y value. So let's take a look at example number 1. Using that definition. So from the graph, we want to determine the domain and the range. So indeed, I have a little arrow that points left forever, which means it's going to continue off the graph to the left towards negative infinity forever. And then we see our graph. We could definitely draw it without ever having to lift our pencil. So then, since it's continuous, our domain is going to be smallest x to largest x. So we have our arrow that points left forever, so our smallest x is going to be negative infinity, and then our graph stops right here at the point 8, negative 5. But we have a hole in our graph, which means we don't include that point. So we can get infinitely close to 8, but never reach 8. So our largest x is going to be at 8, but then we have it not included, so we use the rounded parenthesis. For our range, we're going to do the same thing. We need the smallest y to our largest y. So once again, the lowest point on our graph is going to occur right here. So that gives us our smallest y value is going to be negative 5, once again not included. But now we need our largest y. So we would look right here, and our largest y value occurs at 6. But we actually make it to the point at 6 there. So the ordered pair of that point is negative 1, 6. And since we actually make it to that point, we have to include it. So we use the square bracket to say we include that point. So in terms of our domain, we go from negative infinity to positive 8, not including either, and our range is from negative 5 to 6, including 6, but not including negative 5, because we have that hole in our graph at that point. All right. All right, so our graph is continuous once again, so we need to identify our smallest x and our largest x. So our x that's furthest to the left, this is going to be our smallest, and this is going to be our largest. So our smallest x has a filled-in dot, so for our domain, we're going to have, we start at -8, and we're going to go all the way up to the number 7, and we're going to include it. And we're going to do something similar for our range, but we need to find our smallest y and our largest y. So our smallest y is right here, and our largest y is going to be right here. So our y that's furthest down is right there, and we're going to have 2, and we make it to it, so we do a square bracket, and we make it all the way up here to our number 7. And that is going to be our range. So our smallest y is 2, and our largest y is 7. So that gives us our range is the closed interval to 7, including both of the endpoints. And our domain is -8 included to +7 not included. All right. So now we want to talk about the domain and range, or just the domain of the following function. So before we do, for radical functions, the domain is the solution to the inequality radicand is greater than or equal to 0. And the radicand is the algebraic expression inside the radical. So what we mean by that is the stuff in here is what is referred to as the radicand. So we wish to determine the domain of the following function. F of x equals the square root of 8 minus 2x plus 4. So the first thing we need to identify is our radicand. And we need to solve that inequality. So our radicand is the algebraic expression that's underneath the radical. So in this case, it's 8 minus 2x. And the domain is the solution to the inequality (8 minus 2x) is greater than or equal to 0. So then we minus 8, we minus 8, and we get negative 2x is greater than or equal to negative 8. We divide by negative 2, divide by negative 2, and we get x is less than or equal to 4. Reverse the inequality because we divided by a negative number. So then our domain would go from negative infinity up to and including the number 4. right, so our next type of function that we want to find the domain of is a rational function. So the domain of a rational function where we have f of x is equal to p of x divided by q of x is all real numbers excluding the zeros of q of x. The zeros of q of x are the solutions to the equation q of x is equal to 0. So to find the domain of a rational function p of x over q of x, we know that the domain is going to be all real numbers, but since we can't divide by 0, we take the denominator, in this case named q of x, we set it equal to 0 and solve. And then we exclude the solutions to that equation from the domain. That is not the right problem. There we go, number 3. So to find the domain of f of x equals 1 over x squared minus 64, we identify q of x. So our q of x is going to be x squared minus 16, and we need to exclude the solutions to x squared minus 64 equals 0 from the domain. So this we can factor into x minus 8 times x plus 8 is equal to 0. So our two solutions are x equals 8 or x is equal to negative 8. So then the domain, if we're excluding those solutions, we have all real numbers, but we need to exclude negative 8 and positive 8. So if we remove 2 points from the whole real line, we're going to get 3 separate parts. So the first part of our domain goes from negative infinity to negative 8. Or the middle part goes from negative 8 to positive 8. And then the last part of our domain is over here, where our numbers are bigger than 8. So a good way to visualize this on the number line is visualize the number line as a piece of string. If you take 2 points out of it or you cut it twice, how many pieces of string are you going to have? 3. So your answer is going to contain 3 intervals: the blue interval, the green interval, and the orange interval. For some reason, it's very common, a common error is to forget the interval in the middle when we do this. So don't forget that guy when we have to take out more than 1 point. All right. Now it's your turn. All right, so to resolve u try number 2, we want to determine the domain of the following function. So we have our function each time in both the numerator and the denominator both have a radicand. So we need to solve for radical functions. 2 minus x, which is our radicand in the numerator, needs to be greater than or equal to 0. And our radicand in the denominator is x plus 3, and it also has to be greater than or equal to 0. So we solve by minusing 2, minusing 2. Negative x is greater than or equal to negative 2. Divide by negative 1, divide by negative 1, and x is less than or equal to 2. And we rinse and repeat on the other side by minusing 3, and we get x is greater than or equal to negative 3. But we also have this radical in the denominator. We must also exclude the zeros of the denominator. So looking at our denominator, well, what makes the square root of x plus 3 equal to 0? Well, if we were to solve that, we square both sides and we get x plus 3 equals 0. We minus 3, and that gives us x equals negative 3. But since we're excluding it, x cannot equal negative 3. So we need to resolve our AND type inequality. So to help us visualize that, if we have our number line, we have our negative 3, we have our positive 2, and we have x is less than or equal to positive 2. And we have x is greater than or equal to negative 3. So we shade here. And then we have to exclude x equals negative 3. So that's excluded. So our AND is where those two things overlap, and negative 3 is excluded. So we would get negative 3 in a rounded parenthesis not included up to the number 2 included. So that would be our domain of that problem. So a couple things to keep in mind when we're finding the domain of different functions. So there's not one hard, fast method, right? So as we went through this, when we go back and recap a little bit, when we had a radical function, we took the radicand and we made it greater than or equal to 0. If we have a function that involves division or a rational function, we take the denominator and we set it equal to 0 and solve, and that's what we remove from the domain. So a common thing that goes wrong here is people get these two methods crossed. Don't be Dr. Frankenstein. Don't take half of the first method and half of the second method. One method tells you what you can use. That's for the radical function. For rational functions, we solve for what we can't use. So we're asking and answering two different questions for each type. So make sure that you're keeping those two things straight, because common mistakes are when we Dr. Frankenstein these two methods together and we say for a radical function that the domain is equal to one point that you solve for, and that's not true. So just be a little bit careful as we work on these. All right, the next thing we want to talk about are called piecewise functions. So the idea of a piecewise function is something that looks like this. We have a function f of x. Our notation looks like this, and we're going to have rule 1 and then domain 1. And we're going to have, say, rule 2, and we're going to have domain 2. And rule 3 and domain 3, and so forth. And this can go on forever and ever and ever and ever. So we can have a whole bunch of different rules and a whole bunch of different domains. So in order for us to determine which inputs go where in this, the first thing we have to do is we first check which domain X belongs to. Then we input X into the corresponding rule. So to help this make more sense, let's just go ahead and start on an example. So in this example, in example 4, we have a piecewise function that contains 2 rules. And we have a domain for each of those rules. All right, so let's go ahead, and our first domain is for x values less than or equal to 1. And our second domain is for x values between 1 and 4, not including 1 and 4. So I'm just going to highlight those on my x-axis to help me see where the domain of my function is. So then, if I were asked to find f of -5, I have to determine which domain -5 is in. So I have to answer the question, is -5 less than or equal to 1, or is -5 in between 1 and 4? Well, -5 is definitely less than or equal to 1. So that means we're going to use our red rule. So we're going to use this, so we would get 1/5 times our -5 take away 2. So 1/5 times -5 is -1 minus 2 gives us -3. So f of 5 would be -3. We would do the same thing. We want to calculate f of 0. So now we have to determine, is 0 less than 1, or is 0 between 1 and 4? Well, once again, 0 is less than or equal to 1. So that's going to go into our red rule. So we would have 1/5 times 0 take away 2. And 1/5 times 0 is 0 take away 2 is -2. So f of 0 is -2. And lastly, we want to try f of 1. Once again, we check our domain. Is 1 less than or equal to 1, or is 1 in between 1 and +4? So it's still not in the blue domain. So in this example, we only used the red rule because 1 is less than or equal to 1. So then we would have 1/5 times 1 minus 2, which gives us 1/5 take away 2. So 2 is 10/5. So 1 take away 10/5 is -9/5. And we would get something that looks like this. So now we could plot these points on a graph. So we have some ordered pairs, and all of these ordered pairs came from the red rule, right? So we have the ordered pair, -5, -3. So at -5, I'm down at -3. At 0, I'm at -2. And at 1, I'm at -9/5. So if I play connect the dots, I get something that looks like this. If we look at our blue rule, we didn't use it, but what does the graph of -x² minus 1 look like? Well, that's a parabola, that opens down and is shifted down 1 unit. So we would have a parabola, and we know it opens down, and we're going to shift it down 1 unit. So we would go here. So this point's not really on the graph. Down here, and we're going to get something that looks like this. So that's what our graph would end up looking like. Sorry, and I don't have the arrow that goes forever, because we're going to run out of graph over here somewhere. All right, so let's talk about how we can get more of these points instead of doing it by hand, and by how we can use our graphing device to help us generate these things. So we grab our graphing calculator, and we wish to graph this thing. So we're going to press our y equals button. So when we're doing this on our graphing calculator, we need to wrap our entire rule for each part in parentheses. So I'm going to go parentheses, alpha y equals, I get my 1/5, and I go x, take away 2, and I close my parentheses, and now I need to put my domain in. So I go parenthesis, and I'm going to do x, and in order to get my less than or equal to, I'm going to have to press my second key and math, and we'll notice second math, the secondary function right here is test. So we go second math, and then we're going to choose our less than or equal to, which is choice number 6. And then we close our parentheses. Oops, we don't, because we need a 1 first. Then we close our parentheses, because x is less than or equal to 1. So let's go ahead and check this on our calculator. So we press graph, and we'll see it graphs that line, and then when it gets to +1, what happens? Our graph stops as it's supposed to for that part. So now we want to graph the rest of this, so we go back into our y equals, but before we do, when we have a compound domain, we must split into 2 inequalities. So right now it's written as a 3-part inequality, but remember that's just shorthand for the following. 1 is less than x, and x is less than 4. So let's go back to our calculator. So we have our first part. We go to the end of our inequality, and we separate each part with a plus, and then we rinse and repeat. So we have to put our rule in parentheses. So we go negative x squared, take away 1. We close our parentheses, and then we're going to put each of our domains in separately. So 1, math is less than x, close our parentheses, and then new parentheses, x is less than 4. So now when we graph, we get something that looks like this. And we get a nice graph of our piecewise function. So when we put it into our calculator like this, we can also find our values and verify that we did this correct. So if I scroll up to -5 now, -5 is indeed 3. If I go to 0, I get -2. And if I go to 1, I get -9/5. And I can keep getting more ordered pairs by putting them all into my calculator. I can also use my alpha trace to get my function values as well by selecting y1, If I put in, say, 1 and press enter, my calculator will give me that value. So f evaluated at 1 is equal to -9/5. And if I go graph, as we saw, we get something that matches up with what we had on our calculator. So now that we have a nice picture, we can use this to help us find our domain and our range. So we look at our graph either on our calculator or on our graph, and if I do, we can use that to find our domain and our range. So our domain we don't so much need the picture of because our domains are actually given in the function itself, right? So if we look up at our function, it says x is less than 1 and x goes from 1 to 4. So our domain is going to be from -infinity to +4, not included. Our domain is -infinity to +4, not included. Now our range, what is it going to be? Well, our line goes on forever in this direction, and it's got a positive slope, so as I go to -infinity or to the left forever, my graph is going to go down forever. So my y min is going to be -infinity, and then my largest y is going to be right here. And so what's my largest y value going to be? 2, but of the negative variety. So that is going to be our range. And we can read those values off the graph as well. So if we went second table, we could see where our largest y value was right there, and then it starts going back down again. All right, so to resolve our u-try, let's go ahead and calculate our values. So if we want to calculate g of -5, well, -5 is in between -1 and -5, so we're going to use that rule. So we replace our x with -5, giving us -5. So that domain goes from -5 to -1, so it's right here. Our next value is 0, and we want to calculate g of 0. And 0 is bigger than -1, so we're going to use this rule. So we replace x with 0, but -0 is the same as 0. And that domain is from -1 forever this way. And we're not going to need it in this one, but I will highlight it. So x is less than -5 would be this domain. So that breaks our graph into those 3 distinct parts. Our last one is g of 3. And 3 is also bigger than -1, so we're going to use that rule. We have -3, so we get -3. And that gives us a couple of points. So we have 3, -3, we have 0, 0, and we have -5 and -5. So if we were to analyze this a bit deeper, if I look at my blue rule right here, for all x values less than -5, what is the y value going to be equal to? Well, that function in blue has only one output, and what is the output? 5, right? So everywhere in the blue domain, I'm going to get the horizontal line y equals 5, because that's what my rule says, right? In the yellow domain, I'm graphing y equals x. Well, that's a line with slope 1 and y-intercept 0. So it's going to look something like this. It has slope 1. Oops. So it's going to go slope 1, and it gets to this point, and it stops at -1. And that's my yellow part, and that's just the line y equals x, because that's what my rule is. Then the last part in green is the line y equals negative x. It starts at negative 1, but it doesn't include that point. So at negative 1, we would be at 1, 1, and my line would have slope negative 1 and look like this. So that gives me the graph of my function. And if I put this in my TI calculator, I would indeed be able to get the same picture. Well, let's go ahead and put this guy in. So we put it in, we go parenthesis rule, and then we put its domain. X is less than negative 5. Then to put our next rule in, we go plus. We put our rule in parentheses, and then we put our domain. But remember, for compound domains, we have to break it into two parts. So negative 5 is less than or equal to x. So that's the first part, close, and then we have to do it again. X is less than or equal to negative 1. And then we go plus our last domain, parentheses, negative x. And x is greater than negative 1. We hit graph. We get our horizontal line, that little piece, and exactly the same graph out of our graphing calculator that we got when we created the graph manually. So either way, looking at either of these pictures, we can now find the domain and the range. So are there any x's that aren't in the domain? And the answer is no. So our domain goes from minus infinity to infinity. And we have to be a little more careful with our range. So warning, this function, or this graph, is not continuous. So the range is not smallest y to largest y. So remember, that rule only applies to continuous functions. So now we have to look at our range as what output values does our graph actually make it to. Well, we notice right here on this branch y is equal to 5. On this branch, we have y is in between negative 5 is less than or equal to y is less than or equal to negative 1. And on this branch, we have y is less than or not equal to positive 1. So our domain is the and, or the or of all of these, rather. So if we look at where these ones, negative 5 is less than or equal to y is less than or equal to 1, fits into this one. So we're going to have y is less than 1, but then we have this part that doesn't fit. So our range is y is less than 1, not the or equal to, or y equals 5. So in terms of an interval, that would be from negative infinity to 1, or the interval from 5 to 5. But we have to include 5, so not rounded, but square brackets. And that would be the range of our function. So in this case, it was the or of all three of these, or the union of all three of those sets.